Good morning, students. In the previous lecture, seen about we have started about the asymptotic notation. We just saw the brief about asymptotic notations. So, as mentioned earlier, we had three. We have mainly three different asymptotic notations: big O, big omega, and big theta. So, in this video lecture, we will study in detail about what are those different notations, how they are going to verify based on the input size variable. The first one is big O notation. Big O notation specifies that it represents the upper bound of running time of algorithm, which means upper bound is a highest value. Upper bound represents the maximum time that algorithm is going to represent. So here in this problem, big O always represents the maximum time that algorithm is going to take to run that particular algorithm. Therefore, maximum time always specifies the worst case of an algorithm. Okay, so it is also gives the worst case complexity of an algorithm. So this is most widely used notation for asymptotic notation, because for any particular algorithm, when you want to measure the time complexity of that particular algorithm, worst case complexity is the time specifies, which means that more than this time an algorithm is never going to take. An algorithm is going to take max to max this space specified by big O notation. It returns the highest possible output value for a given input. Now in this given figure, this is a general definition of what is a big O notation. Suppose f of n describes the running time of that algorithm, that f of n is big O of g of n. This is a general equation for asymptotic notation of big O, where f of n is a given running time of an algorithm, whereas g of n represents that it is a there exists a positive constant c and n naught such that f of n lies between these two. In general specific, f of n is actually the runtime of algorithm, whereas your big notation is going to specify your highest maximum value that algorithm can take. So always the running type of that algorithm should be less than or equal to g of 10, where the g of 10 is a big O notation, or it is a function value. So this can be represented by f of n is equals to c into g of n, where c is a constant and this n is for some specific value which should be greater than or equal to n naught. So for till that n naught value, this criteria of equation is going to satisfy. Hope so. If any questions, you can just give me a comments in the give me a queries in the comment section. Next, asymptotic notation is omega. Here omega represents the lower value of asymptotic notation. Means what? As big O represents the upper value, big O represents the lower value. It means that this lower algorithm will never take value less than this lower value. Thus it provides a, you can say this is a best case algorithm, because see every algorithm is said to be the best based on the time complexity that it is going to take. So this algorithm is going to take the less amount of time, so we can say this is a best case of that particular algorithm. Here the execution time serves as a lower bound on the algorithm's time complexity. It is defined as a condition that allows an algorithm to complete a statement executed in a shortened amount of time. Suppose your algorithm is having a time complexity of f of n, big omega notation is g of n. So this can be represented at by f of n is always greater than g of n, or it can also be represented by f of n is equals to c star g of n, or you can also say c star g of n is always to the f of n for all values n greater than equals to n naught. In this given figure also you can see these are the n, y x-axis represents the n values. Your c star g of n is always lesser than f of n, whereas f of n is a complexity of the algorithm for which you want to find out its best case. This is about omega notation. And the last one is a theta notation. We have studied about the lower bound, we have studied about the upper bound. The next one is the average case complexity of that algorithm, and that is represented by theta notation. Theta notation encloses the function from above and below because it is representing, it is having two sections. Either above this or below this, your complexity of algorithm will be represented. Since it is a represents the upper and lower bound of algorithm's running time, it is used to obtain the average case complexity of that particular algorithm. So theta average case, you can add a running times for even possible input combination and take the average in average case. So here if f of n is the algorithm function, then we have two functions g of n above 1 and below 1, whereas above can be represented by constant c1 and below can be represented by constant c2. So you can see in this figure the middle function is your function's time complexity, whereas the below function is the time complexity of lower bound and the above function is the time complexity of upper bound. So in this way, all three notations can be represented for any specific algorithm. Every algorithm henceforth can be represented either in the uh, lowest case, average case and uppercase notation with the help of these three different asymptotic notations. So now we will end with the first chapter. So I will stop this video.